Hello, am I audible? It's okay. So the last class we have finished Faraday's law, right? We have to do Lenz's law today. So Nabil, what is Nabil Khan? What is magnetic flux, Nabil? Nabil, what do you mean by magnetic flux?
So number of magnetic field lines passing through a closed area.
Not a closed area. When you have closed area, then your flux will be zero. Through an area, any area.
Yes, sir.
That if that area is closed, then your flux will be zero.
Through the surface area, right?
Yeah, through a surface area. Okay, and how we calculate flux? Like if you have magnetic field, then how will you calculate flux?
Sir, first integral, no, just B dot ds. Sir.
Yeah, flux
A
is
is
B
area
dot ds.
and B is a magnetic.
BA cos theta.
Yeah, BA cos theta, B dot is B is magnetic field, S is the area vector. Yashika, what is theta? When we write B as cos theta as the formula for flux, what is theta here?
Sir, area between B and area vector.
Yeah, angle between B and area vector. And what is the direction of area vector?
Sir, perpendicular to the surface.
Perpendicular to the plane of area. Very good. So Noah, what does Faraday's law says? Noah Akhtar, what does Faraday's law says, Noah?
Sir, it says induced EMF is equal to rate
Arpit,
of
what is Faraday's law?
Sir, it says that
Arpit.
whenever magnetic.
Arpit? Sorry?
Sir, it says that whenever magnetic flux linked with the coil change and EMF is induced in it. Sir, if circuit is closed, then the current is also induced in the circuit, closed circuit.
Yeah. So whenever magnetic flux is BA cos theta, right? So whenever magnetic flux changes, some EMF gets induced in the circuit. So we are talking about an alternate source of EMF. So what is the usual source of EMF?
Cells and batteries.
Cells and batteries. When we do Faraday's law, we are talking about an alternate source, which is not cell or battery. Usually the generator, the dynamo. The dynamos are based on Faraday's law. And dynamo's flux changes, and due to change in flux, you get some EMF. So we have finished up to here. Now we will start next one. So this was the expression of induced EMF, right? Induced EMF is this. Induced EMF is minus of d phi over dt. This negative sign, we have discussed that this negative sign is Lenz's law. So if your system obeys Lenz's law, that means your system obeys conservation of energy. Any system cannot just violate the law of conservation of energy. So in all your cases of induced EMF, this Lenz's law should be obeyed. Now let's see what is Lenz's law. What is the cause of induced EMF, Yashika?
Sir, change in magnetic flux.
Change in magnetic flux. So the Lenz's law says the induced EMF will oppose its cause. So Lenz's law says that induced EMF will oppose its cause. So how flux changes? Flux can change in two ways. Like flux can increase or flux can decrease. So the Lenz's law says if flux increases, then induced EMF will try to decrease the flux. And if flux decreases, then induced EMF will try to increase it. That's Lenz's law. I'm repeating again. The cause of induced EMF is change in flux. The Lenz's law says the direction of induced current or induced EMF is such that it opposes its cause. It opposes its cause means it's opposed change in flux. And how flux can change? Flux can either increase or flux can either decrease. So induced EMF will oppose both. It will oppose increase in flux as well as it will oppose decrease in flux. So if you have a circuit, if the flux is decreasing in that circuit, then Lenz's law says induced EMF will try to increase that flux. If flux increases in a circuit, flux is increasing, then the Lenz's law says induced EMF and hence induced current will try to decrease it. How can it increase or decrease? That we will discuss in the next section, in the questions of Lenz's law. So it gives the direction of induced current and polarity of induced EMF. So according to Lenz's law, direction of induced current is such that it opposes its cause, that is oppose change in flux. So if flux is increasing, then induced current will try to decrease it. If flux is decreasing, then induced current will try to increase it. And also, Lenz's law is in accordance with the law of conservation of energy. If your system follows Lenz's law, if it obeys Lenz's law, that means it obeys conservation of energy also. If your system violates Lenz's law, that means it's violating law of conservation of energy also. Here, this negative sign is representing Lenz's law. Note it down. Lenz's law. So this is the first topic of today's class. The first topic of today's lecture, Lenz's law.
Sir, Lenz's law keeps flux constant.
No, Lenz's law, it can't keep flux constant. It just try to change the, or you can say it can try to reverse the change in flux. If it is increasing, it's try to decrease it, but it can't keep it constant, because if it makes the flux constant, then induced EMF will be zero. It don't make it constant. It just try to reverse the change. If it is increasing, it tries to decrease it. If it's decreasing, it tries to increase it.
Okay.
Because if it makes it constant, then there will be no induced EMF. There won't be any induced current. Yes, can I scroll it further?
No, 1 minute, sir.
Just the name of the topic, Lenz's law.
Okay, sir.
Sir,
Mhm.
sir, what do we
Yes,
mean
sir.
by opposing its cause?
Induced EMF or induced current, it's opposing its cause. Why it opposes its cause?
Yes, sir. Yes.
Arpit, you're asking why it's opposed its cause.
Yes, sir. I am asking that only.
If it doesn't oppose, then it will violate the conservation of energy. It opposes its cause just to conserve energy. We'll see in few examples. You will notice if you don't follow Ohm's or this Lenz's law, then energy conservation gets violated. So the answer of your question is it's oppose its cause just to conserve energy. Can I scroll it? Minashi, you were absent for last few classes
Yes, sir.
due to your exam or some other reason?
I was in India, so most of the days I won't be at my home.
Okay, so you're back in Bahrain.
Yes, sir.
So when are your exams? Your midterm exams?
In September. This month.
And what topic are you doing in school?
I'm doing magnetism, magnetic field.
Okay. And Nabil Ahmed, you, what topic are you doing in your school right now?
So we're doing a moving called galvanometer, sir.
Moving galvanometer. Nabil Khan, you?
So today we did Bart's law.
Arts Law. Arpit?
Sir, we are on the same track.
Same
like
track.
what we are doing in the classes.
This thing, electromagnetic induction. no?
Yes, so that's parallel. So we did the lens law today.
Okay. Hishma,
Yes, sir.
what topic are you doing in your school nowadays?
Sir, we finished electromagnetic induction.
6th chapter. Okay. Saifullah,
So we finished Gauss theorem and magnetism.
okay, you're doing the same chapter. Noah,
So done with AC.
you're done with AC.
Yes, sir.
Okay. Uneeb,
Sir, school.
hmm. Yes, school में.
Sir, AC चल रहा है.
Okay, ज़्यादा दूर नहीं है. Yashika, same.
Yes, sir. We at the same.
So Lenz's law is this. Now, to solve questions of Lenz's law, you should know some right-hand rules that we did in the chapter of magnetics in the last chapter. So let's discuss those rules. So the first thing that we did is, if the current in the coil is clockwise, that means the top face of the coil will behave like the south pole of the magnet. And if the current in the coil is anti-clockwise, then the top face will behave like the north pole of the magnet. This is what we do in magnetic movement. So I'm repeating it again. If the current is clockwise, that means the top face will behave like the south pole. If the current is anti-clockwise, that will mean that the top face will behave like the north pole of the magnet. So the type 1 question, the questions that you will get in Lenz's law, I divide those questions into 3 categories. So all questions will fit in one of those categories. The first category is, you will have a magnet, and along with magnet, you will have a coil. So we'll have a magnet and a coil. So this is your coil. Your magnet is stationary. Is there any flux linked with the coil, Nabil? This magnet is placed near the coil. Is there any flux linked with the coil?
No, sir.
No, sir.
Because it's stationary.
No. Yoshika, is there any flux linked with the coil?
No, sir.
Yes. Yes,
Sir,
because
there is flux, sir.
see, you have magnet.
Because
This magnet will generate its magnetic field, right? So some
sir.
flux will pass through the coil. So some flux is linked with the coil. When you move this magnet, so if this magnet is stationary, then the flux is constant, because flux is BA cos theta. If the magnet is stationary, then your flux is constant. B constant, A constant, theta constant, flux is constant. If flux is constant, Hishma, then how much is the induced EMF? Hishma, what does Faraday's law says if flux is constant, and what is the induced EMF in the coil?
So the EMF will also be constant.
Sorry?
The EMF will also be constant.
No, EMF will be 0. You have EMF only if flux change. Good, Nabil. You have EMF only if flux changes. If flux is not changing, then you don't have EMF. For EMF, change of flux is important. So if this magnet is stationary, there is no induced EMF. Now this magnet starts moving towards the coil. So when the magnet starts moving towards the coil, the magnetic field will increase. The magnetic field associated with the coil will increase. And due to increase in this magnetic field, flux linked with the coil will increase, and there will be some induced EMF. Now you're supposed to calculate that induced EMF. So you have to get the direction of that induced current and the polarity of induced EMF. To get the direction of induced current, we use Lenz's law. For Lenz's law, you have to first identify the cause due to which flux is changing. So I identify the cause in this way, like the cause is approaching North Pole. North Pole is approaching the coil. So the cause is approaching North Pole. That is the cause due to which the flux is changing. What does Lenz's law says, Uneeb? What does Lenz's law says? The cause is approaching flux. Then what induced current will do? It will support its cause or it will oppose its cause?
Oppose.
It will oppose its cause. So to oppose its cause, this coil should repel this north pole, because north pole is approaching the coil. Coil will try to oppose its cause. The cause is approaching north pole. So coil will repel this magnet. So to repel this magnet, what you need a south pole or a north pole?
North.
To repel this magnet, you need a north pole. So that means this particular face of the coil will behave like the north pole. So the direction of current in the coil is this way. The current is going anti-clockwise. This is the direction of current in the coil. I'm repeating it again. To solve these type of questions, when you have a magnet and a coil, then identify the cause. The cause is approaching north pole. So if the north pole is approaching, then coil will try to repel north pole. To repel north pole, this coil will require a north pole. So the face, this face, the face towards the magnet will behave like a north pole. So the current will be anti-clockwise. So in the coil, the direction of current is anti-clockwise. Okay, just tell me one thing, Noah. Clockwise and anti-clockwise are absolute or they are relative directions? Like if you have an observer here, for this observer, current is anti-clockwise. What about this observer? Current will be anti-clockwise or the direction of current will change? Noah.
Sir, it will be clockwise.
It will be clockwise. See, clockwise or anti-clockwise will depend. Like if I give you a coil and I say, okay, the direction of current in the coil is clockwise. But from your end, it could be clockwise, but from my end, it will be anti-clockwise. So clockwise and anti-clockwise depends who is observing. So here also, if I'm saying the direction of current in the coil is anti-clockwise, but this anti-clockwise direction will depend who is viewing this coil. So the anti-clockwise direction is with respect to this eye, the eye which is towards the magnet. If you place your eye here, then what will be the direction with respect to this eye? Anti-clockwise or it will be clockwise? First, what will be the direction for this eye? Clockwise or anti-clockwise? Yes, Nabil. Ahmed.
Clockwise.
It will be clockwise, right? This will be clockwise. So if in the question I is given, then write your answer with respect to that I. This is I. It does not look like I, but this is an I. If I is not given, then assume your eye towards the magnet. If I is not given, then assume that your eye is towards the magnet. So coil will try to repel it, face of coil towards magnet will be north and the current will be anti-clockwise. This is how we solve these types of problems. Now, if I take this particular problem, Nabil Khan, what is the cause of changing flux in this coil? Nabil Khan, what is the cause here? Is north pole approaching the coil or it's moving away from the coil?
It's approaching.
It's, sorry?
North pole is moving away.
Moving away. So what this coil will try? It will try to repel the north pole, it will try to attract the north pole. Nabil Khan again.
It will repel.
Repel, it's going away. The coil will try to oppose its cause. The cause is this motion. If this becomes north, then it will repel it. It's not cause. It's not opposition. It's support. Na? If this coil repel this magnet, that means the coil is supporting the motion of the magnet. But the coil will support or it will oppose?
Oppose.
So for opposition, what this coil will do? It will repel the magnet. It will attract the magnet. It will attract the magnet. For attraction, what you need?
South
You
pole.
need a south pole. So the direction of current will be clockwise here. Clear, everyone?
Yes, sir.
Yes.
But it will repel, right?
Why it will repel? See, it not always it repel. It just try to oppose the cause. See here. Here, north pole was trying to approach the coil. So what this coil do? It will oppose its coil. It's approaching, so it try to repel it. Here, it's already going away from the coil. So if coil repel it, it's supporting its motion. No? Coil will oppose every time it will oppose. So the magnet is going away from the coil. So the coil will attract it. If the magnet is going towards the coil, then coil will repel it away from it. Nabil, clear now?
Yes, sir. Yes, sir. Okay.
So the current direction of current is clockwise. South will be the pole and the direction of current will be clockwise. So this direction is clockwise for which observer? For this observer, huh? The observer which is towards the magnet. For this observer, it's clockwise. So in all our questions, we always put observer towards the magnet. So its cause is receding north pole. Coil will try to attract north pole. To attract north pole, it needs south pole. So current is clockwise. Okay, now let me rub this thing first. One second, I'm just rubbing the solution. Otherwise. So you have two coils, coil 1 and coil 2. You have to decide the direction of induced current in both the coils. So Hishma, for coil 1, what is the cause? Approaching south pole or receding south pole? Hishma, for coil 1, what is the cause of induced EMF? Approaching south pole or receding south pole?
As the south pole is moving away from.
So if it is moving away from the coil, what this coil will try? It will try to repel the south pole, it will try to attract the south pole.
It will try to attract the
To attract south pole, which pole you need?
north pole.
North pole. So this will be north pole. If it is north pole, that means direction of current will be anti-clockwise. Yashika, what this second coil will try? It will try to
To
attract,
oppose.
to oppose. So how will it oppose this magnet?
Sir, by repelling it.
Repelling the north pole. To repel north pole, which pole you need?
Sir,
You need
not
north
full.
North pole. So the direction of current will be anti-clockwise. So these were the type 1 questions on Lenz law. Just note it down. See, these explanations that I am giving here, these explanations that I am writing, these explanations are not required in your school exams. You just have to write whether it's clockwise or anti-clockwise. But if you write these explanations, they will help you to revise the concepts. This is type 1 question, magnet and coil. Note it down. Miraj, you are again late.
Sir, actually, sir, I have my half yearlies tomorrow.
It's okay. Of what subject? Which subject?
So today was chemistry, sir, and then sir, tomorrow is for English.
It's okay. Akshay, you can take screenshot. Huh? We started Lenz law.
Okay.
You can take screenshot. We started Lenz law.
Done, sir.
Now you can write.
Okay. Sir.
सर इस वाले क्वेश्चन में मतलब गिवन क्या क्या है?
It's given that the magnet is moving towards the coil. North pole is approaching the coil.
Okay, sir.
The direction of movement will be given. A coil will be given, and it will be given whether the north pole is approaching the coil or it's going away from the coil. Yes, can I scroll it now?
Yes,
Yes,
sir.
sir.
So, 1 minute. Done.
I'm repeating again, there's no need to write these steps in your final exams. The question will only ask the direction of the current. Can I scroll it now?
Sir, is it given कि coil का ये वाला जो face है वो south pole है?
नहीं, ये तो डिसाइड करना है. यही तो आप डिसाइड कर रहे हो. आप ऐसे डिसाइड करो. नॉर्थ पोल इज गोइंग अवे फ्रॉम द कॉइल, राइट? So the coil will try to attract, will try to oppose the motion of the magnet. So the coil will try to attract the north pole. To attract
Okay.
north pole, coil will induce a south pole. This is
Okay.
what you have to decide. Through this south pole only you can decide the direction of current. Can I scroll it? So I believe everyone have written up to here. Huh?
So 1 minute, sir.
Yes, everyone have written.
Yes, sir.
Okay, in the next type of questions, you will use this logic. Like if you have two magnetic fields which are acting in opposite directions, so when you add them up vectorically, they will actually get subtract out and the net magnetic field will decrease. See, 1 Tesla and 3 Tesla, they are acting in opposite directions. The net magnetic field will be 7 Tesla. If both the magnetic fields are in same direction, then they gets added up. 10 Tesla and 3 Tesla will get added up and 13 Tesla. So if you have a magnetic field here, like you have B1, and I ask you to decrease the strength of magnetic field by applying another magnetic field, then we'll apply that magnetic field in opposite direction. You have one magnetic, see, you have one magnetic field in one direction. I'm asking you to decrease the net strength of magnetic field. So what you will do, you will apply another magnetic field in opposite direction. If you have a magnetic field in one direction, and I ask you to apply another magnetic field, so that the net magnetic field increases. So what you will do, you will apply another magnetic field in the direction of the first magnetic field. So the summary is, if two magnetic fields are acting in opposite direction, then the net will decrease. If they're acting in same direction, then the net will increase. So the third type of questions will use one more logic. This we have studied in magnetics. There's one relation that we did in magnetics. Just 1 second, we'll take some time to refresh. So in magnetics, we did a modified right-hand thumb rule to get the direction of current for a circular coil. In magnetics, we did the right-hand thumb rule for a circular coil. Does anyone remember? Noah? What was the direction to get the direction rule for the direction of magnetic field for a circular coil? Noah?
So Fleming's right? Rule.
No, not Fleming's rule. We don't use Fleming's rule. We never use Fleming's rule. Nabil Ahmed, do you remember the rule for the direction of magnetic field for a circular coil? No. Does anyone else remember in this class the rule for the direction of magnetic field if you have a circular coil? Okay, no one remember.
So rotating the palm along the direction of the current of the right hand.
So if this is a
The
coil,
right hand thumb rule.
right hand thumb rule modified, like if this is current, you will curl your finger along the sense of current. If the current is clockwise, you will curl your finger clockwise. The thumb will give the direction of magnetic field. So the fingers are clockwise, thumb is going inwards. That means the direction of magnetic field is inwards. Your magnetic field is going in inwards direction. This is how you apply right hand thumb rule, right? So if the current is clockwise, you apply right hand thumb rule, your magnetic field is going inwards. Here, when you use this law in Lenz's law, you will be the direction of magnetic field will be known. You're supposed to calculate the direction of current. Like if this is a coil, I give you the direction of magnetic field. I told you that magnetic field is inwards. It's given that magnetic field is inwards. You just have to decide the direction of induced current. So what you will do, just take your right hand, put your thumb in the direction of magnetic field. It's inwards. Put your thumb inwards. How your fingers are curling, is it clockwise or anti-clockwise? If you put your thumb in inverse direction, then your finger should go in clockwise sense. So the direction of induced current will be clockwise. So when we use right hand thumb rule in Lenz's law, the direction of magnetic field will be known and you're supposed to decide the direction of current. So the law gets modified, like put your thumb of right hand along magnetic field curvature of finger will give current. So when you use right hand thumb rule here, the direction of the thumb will be given. The direction of magnetic field would be given. Just have to decide the direction of current. So this is the first type of question. The first question of type 2. In type 2 question, magnetic field plus coil is given. The direction of the magnetic field is inverse. You are taking this coil here in this direction. So you have to decide the direction of the induced current. See, for different types of questions, the logic would be different. In the type 1 question, you have a magnet and a coil. In type 2 question, you have magnetic field and coil. The logic is different. So here what we can see that the coil is entering in the magnetic field. So when coil is entering in the magnetic field, that means area linked with the magnetic field is increasing, which means the flux is increasing here. So flux linked with the coil is increasing. So Hishma, what do you think? Induced EMF will try to increase flux or will try to decrease flux? Hishma. Flux is increasing. What does induced current will try? It will try to increase the flux or it will try to decrease the flux? Minash. Yeah, it opposes, so it will try to decrease the flux. So induced current will try to decrease flux. To decrease flux, it have induced magnetic field. So when flux changes, there will be some induced current in the coil. We know that there will be some induced current in the coil. We just don't know the direction of induced current. So if we have induced current, that means we have induced magnetic field also. We just have to decide the direction of induced magnetic field. The direction could be inwards or the direction could be outward. You just have to decide what is the direction. So, Unib, what do you think? What should be the direction of induced magnetic field? Induced magnetic field should be inwards or it should be outwards? Unib, what should be the direction of induced magnetic field? It should be inwards or it should be outwards?
Sir, outward.
Why outwards? Why? Why you said outwards? Logic? It's because you have two options, either inwards or outwards. It's just outwards, or you have some logic behind outwards.
Sir, maybe it's moving like this.
No. See, the answer of Unib is correct. Induced magnetic field will be outwards. Can anyone explain why it should be outwards?
The right hand thumb rule, sir.
No. We don't know the direction of induced current yet. How will you apply right hand thumb rule? We don't know where induced current is.
So to
Anti-clockwise.
oppose.
No, we don't know the direction of induced current. See, first of all, we will decide the direction of magnetic field. Then we will decide the direction of induced current. Listen very carefully. The coil is entering in the coil. So the flux with the coil is increasing. Due to change in flux, you will have an induced current and will try to decrease flux. To decrease flux, it will generate an induced magnetic field. So if direction of induced magnetic field is opposite to that of the initial field, then what will happen? The net field will increase or field will decrease? If both the fields are in opposite direction, then what will happen? Field will increase or it will decrease? First.
Increase.
It will decrease. See, if two fields are in opposite direction, they will cancel out each other. They get subtract out at least. So the net field will decrease. So induced current will generate induced magnetic field. And what will be the direction of induced magnetic field? In a direction which is opposite to that of the original field. If original field is inwards, that means induced field should be outwards. So now you have that induced magnetic field will be outwards. Now apply right hand thumb rule. Just take your right hand, place your thumb in the outwards direction. What's the curvature of your finger? Is it clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise. The curvature of finger will be anti-clockwise. So it tells you that the direction of induced current is now anti-clockwise. This is how we use Lenz's law. So I'm repeating it again. Your coil is entering in the magnetic field. So when your coil enters in the magnetic field, that means flux linked with the coil will increase. So if flux linked with the coil will increase, that means some induced current will be there. The induced current will try to oppose the change in flux. So it will try to decrease flux. So to decrease flux, that induced current will generate one induced magnetic field. The direction of that induced magnetic field will be opposite of this field, so that both the fields gets cancelled out each other. If magnetic field decreases, then the flux will decrease. So induced magnetic field is outwards, and you can apply right hand thumb rule and you'll get the direction is anti-clockwise. Note it down. Then we'll do another question on the same type. Do one more question of the same type, but at least note it down.
सर पहले वो ऊपर वाला नहीं
अच्छा, ये तो लिखने की जरूरत नहीं, तो तुम समझा रहे थे यहाँ से.
सर ये जो आपने करंट की डायरेक्शन एंटी क्लॉकवाइज बनाई हुई है ये इंड्यूस्ड है फिर पहले से करंट
इंड्यूस करंट है, इंड्यूस करंट, इंड्यूस करंट. Umar, you have missed the major portion of Lenz's law. Like this, the discussion that we are doing right now is based on the previous discussion that we are doing for the last 40 minutes. Umar, the class timings are 8:30. It's not 9:15. I can repeat this numerical, but the logic that we are using is this numerical is what we are discussing for the last 40 minutes. So here the coil is going inside the magnetic field. So if a coil is going inside the magnetic field, the flux linked with the magnetic field will increase. The Lenz's law says the induced EMF will try to oppose the change in flux. So the flux is increasing. The induced current will try to decrease flux. So if you have induced current in the coil, you will have some induced magnetic field. If original magnetic field is inverse and induced magnetic field will try to decrease flux, the direction of induced magnetic field should be outwards. So both the fields are in opposite direction. Original is inwards, induced is outwards. So if you have induced magnetic field in the outwards direction, then just use right hand thumb rule. Put your thumb in the direction outwards and the curvature of finger will be anti-clockwise. Can I scroll it?
No, sir.
And again, all these steps that I'm writing, you need not write these steps in your final exam. The final exams just have to write whether the current is clockwise or it's anti-clockwise. But these steps are important when you revise this topic. Tell me once you all have written, I will scroll it up.
So what is it? So BI
BI is induced magnetic field.
in the last point. So
Yeah, this one, no? This BI is induced magnetic field. B subscript I, this means induced magnetic.
yes.
Okay, now so do this question. See, the coil is triangular. It's coming out of the magnetic field. The magnetic field is outwards. You have to decide the direction of induced current. So write each and every step. Flux is increasing or decreasing. What should be the direction of induced magnetic field? Then what will be the direction of induced current? Do it. It's going out of the coil. You have 2 minutes, then I will do this question. If you can do this, that means you know Lenz's law now.
So what should we find out here?
The direction of induced current. Okay, see. So the first step is, okay, Umar, let's see. So what is happening with the flux, Nabil? Flux is increasing or decreasing, Nabil Khan? What happens with the flux linked with this triangular coil, Nabil? The flux
Sir,
is increasing
decreasing.
or it's decreasing?
Sir, decreasing. Sir, decreasing.
Flux is decreasing. It's going out of the magnetic field, so flux is decreasing. What will induce current will try? Induced current will try to oppose its cause. It will try to increase the flux. So induced current will try to increase the flux. How will it increase the flux? It will increase the flux by inducing a magnetic field. So it will induce a magnetic field. So what should be the direction of induced magnetic field? It will support the magnetic field. Flux the induced current will try to increase the flux. So induced current will try to increase the direction of magnetic field. To increase the strength of magnetic field, your original magnetic field and induced magnetic field should be in same direction. If original is outwards, that means induced should also be outwards. Then only they can add it up. The strength of magnetic field will increase and the strength of this flux will increase. So induced current should be anti-clockwise. So the current is anti-clockwise. So magnetic field is outwards, you can apply right-hand thumb rule. Just put your thumb outward, the direction of the current is anti-clockwise. Good, Uma, your answer was correct. So it will be anti-clockwise. This is it. Just note it down. That's type 2 question. We have one more case, type 3, and then it's over. Alia, Minashi, is it clear?
Yes, sir.
Noha, see, the original magnetic field is outwards, and the flux is decreasing. So induced current is trying to increase the flux. To increase the flux, the induced magnetic field and the direction of original magnetic field should be same. Original magnetic field is outwards, so induced magnetic field should also be outwards. Both the fields are in same direction. So if your induced magnetic field is outwards, then your current is anti-clockwise. Yes, everyone have written?
Yes.
Okay. Okay. Just tell me once you have written. Okay, let's move on to the next thing. Next question. For the next type of question, we will use some rules that we studied in chapter number 4, direction of field due to a long current carrying wire. So for a current carrying wire, we used a screw rule. If you can remember, this is the application of Biot-Savart's law, long wire. For long wire, we used to use screw rule. Screw rule says, just place your thumb in the direction of current and the curvature of finger will give the direction of magnetic field. So when you take this, the curvature of finger is clockwise. So here the magnetic field is inwards and here the magnetic field is outwards. We already finished this thing in chapter number 4, application of Biot-Savart's law. So in the type 3 questions, the type 3 says this is current which is increasing. Near to this current carrying wire, rectangular coil is placed, you're supposed to decide the direction of induced current in this coil. First of all, there is no movement. This coil is not moving. Just give me 1 second. So this is the wire is carrying some current. This wire will generate some magnetic field. Here, the direction of magnetic field will be outwards. If you apply right hand screw rule, just place your thumb in the direction of current, the curvature of finger is outwards. The direction of current here is outwards. Sorry, not current. The direction of magnetic field here is outwards. This is not the induced magnetic field. This is the external magnetic field generated by this wire, B. In this question, this outwards magnetic field was given. But in type 3, using right hand thumb rule, you have to decide the direction of this magnetic field. Then you will decide what's happening with the flux, whether flux is increasing or decreasing. See, this magnetic field depends upon current through the wire. This is what we did in Biot-Savart's law. So if your current is increasing, that means magnetic field is increasing. So if current is increasing, then strength of magnetic field will also increase. If magnetic field increase, that means flux will increase. The induced current will try to decrease flux. To decrease flux, the original magnetic field is outwards, so the induced magnetic field will be inwards. If the induced magnetic field is inwards, then direction of current is clockwise. The current will be in the clockwise direction. This is the direction of induced current. If this current is decreasing, then the induced magnetic field will be outwards only and the direction of current will be anti-clockwise. This is type 3 question. So in type 3 question, you have to first decide the direction of external field, then you will decide the direction of induced magnetic. If you look at the difference between type 2 and type 3, in type 2, the direction of this original magnetic field or the external magnetic field is given. But in type 3, you first have to decide the direction of external magnetic field. Then you will decide flux, then you will decide induced magnetic field, and then you will decide the direction of induced current. Is it clear, everyone? Arpit, Minashi, Yashika?
Yes, sir.
No.
You can just scroll up for a second.
Up. This is
Yes,
repetition of what we
yes,
did
I
in
did.
Biot-Savart's. Right. Can I scroll it?
1 minute, sir.
6 minutes.
Are you getting these directions? Saifullah, Noah, Ishma.
Yes, sir.
Yes, sir.
See, Umar, the direction of the external magnetic field is given by right-hand thumb rule. We place a thumb in the direction of current and the curvature of finger will give the direction of magnetic field. So if you place it in this way, then the curvature is coming outwards. That means the external magnetic field is in the outwards direction. Also, the current is increasing. If the current is increasing, then magnetic field will also increase. B is directly proportional to I. So if magnetic field is increasing, that means the flux linked with the coil is increasing. And the coil will try to decrease flux. So if the external magnetic field is in the outwards direction, the induced magnetic field will be inverse. So you will have an induced magnetic field in the inverse direction. The curvature of finger will give the direction of current. It will give the direction of current to be clockwise. Yes, then only it can decrease. The fields are vector quantities. They can only decrease if both are in opposite directions. So, sorry, to increase flux, both should be in same direction. If they are in opposite direction, then fields will decrease. They will subtract out. Now you have fields to vector quantities which are acting in opposite direction. So the net will be B1 minus B2. It decreases. To increase, they should be in same direction. See the next question. The next question says, this is a coil and this coil is moving within the magnetic field. It's neither going inside the magnetic field nor it's going outwards outside the magnetic field. This is moving within the magnetic field only. So if the coil is moving within the magnetic field, that means there is no change in flux linked with the coil. So if there is no change in flux, that means flux is constant. Flux is constant. There is no induced current. You will have induced current only if the coil enters the magnetic field or it goes out of the magnetic field. If the coil is within the magnetic field, that means there is no change in flux. No change in flux means no induced current or no induced current. Clear, everyone? Just note it down. Just one last question, then this Lenz's law is over. We'll start motionally. Umar, if this coil is moving within the magnetic field, that means flux linked with the magnetic field is not changing. Lenz's law says EMF will induce only if flux changes. Flux is not changing, so there will be no EMF, there won't be any current. Umar, you have to attend this class at the time. The time is 8:30. If you miss 40-45 minutes of lecture, then it's very difficult for you to follow the complete lecture. Sometimes the whole class is based on the first 20-25 minute lecture. You have to be on time. I didn't get you. Obviously, the link for the class which is starting at 8:30 is same, na? The link point. What is link, Abdullah? Umar? What do you mean by link is same? See, the fixes magnetic field into area into cos theta. So B is not changing because your coil is within the magnetic field only. A is not changing, theta is not changing. That's why flux is not changing. If flux is not changing, that means there is no induced EMF, no current. Okay, what about this? If there is a coil in the magnetic field and this coil is to decide why the direction of induced current is anti-clockwise. This coil is not moving inside the magnetic field, but it is expanding. Due to its expansion, its area is increasing. Sorry, some network issues. So this will be your homework. If the coil is not moving anywhere in the magnetic field, it's expanding. So its area is increasing, flux is increasing, the induced current will be anti-clockwise. That's your homework. Okay. That's your homework. The next logic that you will be using in the next question, the logic that we did in chapter number 4 is, if the current is clockwise and you curl your finger along the sense of current, the thumb will give the direction of magnetic field. Okay, do one thing, just note it down. Did you write this question? Akshay, Nabil, Ishma, did you note this question?
Yes, sir, this
Yes,
is
sir.
done.
This is done. Okay. Did you note this question?
No, sir.
Just note it down. This is your homework, huh?
So can you
The
score
coil
it?
is yes. More or that's enough?
No, it's not. Done.
It's okay. Note it down. So if the coil is expanding in the magnetic field, it's not moving, but due to the expansion, area is increasing, flux is increasing. So there will be some induced current here also. The next question is this, huh? So
1 minute, can you go up?
yes, 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 I will. Yes, yes.
Yes, sir, done.
It's okay. It's okay, Nadine. Abil, I'm sharing here only. Yeah? I'm sharing here only. Okay, so write down this question. Key is just close. Second part is after long time being closed, key is just open. So these are the three cases under which you have to decide the direction of induced current in coil 2. The first one is when you just close the key after a long time being closed, when you just open the key.
Sir, could
Note
you
it
show the
down.
above question little bit, sir?
Which
The
one?
above question.
Previous one.
Yes, sir.
This. The answer is anti-clockwise. I just have to decide why this is anti-clockwise. Yes, Nabil, written.
Yes, sir.
Now, this is the last question on Lenz's law. Just note down this question and write your answer in chat room. Please, everyone, write your answer in chat room. The question has three parts. The first one is when the key is just closed after a long time being closed, when the key is just open, just write the direction of induced current in all cases. Yes. Did you do this question?
Yes, sir.
Answers? Please write your answers in chat room. Please write your answers in chat room. Answers of all three parts. Okay. And what about the second part? Alia? See, in the first part, when you just close the key, see, when you close the key, the current starts flowing in the coil 1. The current is going clockwise. So, Minashi, if the current is going clockwise, then what is the direction of the external magnetic field? Minashi, in coil 1, the current is going clockwise. Then what is the direction of magnetic field here?
Toward
Again, I'm asking, this is coil 1. The current is going clockwise in coil 1. What is the direction of magnetic field here? You apply right in thumb rule. Just curl your finger along the sense of current. Where is the thumb going?
toward
The thumb is going inwards, right?
inward.
So the magnetic field is
So
inward. This
what does
is
it
like,
mean when you're saying after long time being closed?
sorry,
Sir, what does it
I'm
mean?
coming to it. I'm
saying
coming to it.
after
I'm
long
coming to it.
time?
I'm coming to it long time. First of all, when you
Yes,
just shut down your key, the external magnetic field is inwards. The current is going clockwise. Now, when you just close the key, then your current starts increasing, right? When you just close the key, the first part, the current increase from 0 to a maximum value. When current increases, this magnetic field increases, the flux increases. There will be an induced current in the coil, and that induced current will try to decrease flux. So what will be the direction of induced magnetic field here? Akshay, what should be the direction of induced magnetic field in this case?
It will be opposite.
It will be opposite. So inwards or outwards?
So outwards.
Outwards. So induced magnetic field will be outwards. So induced current will be anti-clockwise.
Yes. Sir, I have sent the answer.
Okay, good. Now, in the second part, after a long time B is closed, after a long time, the current saturates, the current becomes constant. So when the current becomes constant, your flux also becomes constant. For a long time, the current becomes constant. Your phi is also constant. So what should be induced current? Your induced current is 0. You will have current only if flux is constant. So Nabil, do you get what does this long time being closed means? When you
Yes, sir.
just close the key, then after a few seconds, your current settle down to a maximum value. Your flux current constant, flux constant, current is 0. The next is when it is just opened. So when you just open the key, the current starts decreasing, flux decreasing. What will be the direction of induced magnetic field now, Noah? When you just open the key, what is the direction of induced magnetic field? It will be inwards or outwards? Noah Akhtar.
Sir, inwards.
Sorry?
Inwards.
Inwards. So induced magnetic field will be inwards, your current will be clockwise. The reason is when you open the key, the flux will decrease. Induced current will try to increase flux. To increase flux, the induced magnetic field should be inwards. Current is clockwise. That's the answer. Just note it down. So that's about Lenz's law. Lenz's law is over. Now we'll start motional EMF. Note it down first. Yes, can I scroll it now?
1 minute.
From 0 to maximum value, Umar. Okay, so motional EMF, we'll start motional EMF in the next class. We'll do that JE need stuff now. We'll be revising current electricity now. So I need just 2 more lectures for EMI, 1 lecture for motional EMF and another is for induction. There's just 2 topics left. So I'll be starting the revision of current again. So we have finished. Yes, we were doing current electricity. So we have finished in this revision. We have finished questions up to this Kirchhoff law. We have discussed RC circuit. We have discussed charging of capacitor. Okay, the discharging of capacitor was good. So this is only that's the only topic which is in JE syllabus, but not in class 12 syllabus. That is REC circuit. The another topic is potentiometer. So the 2 topics which are in JE syllabus but not in CBSE syllabus are RC circuit and potentiometer. So let's recall this thing once again. So in RC circuit, you have a capacitor and a resistor and you connect it through a cell and you connect this key. As you close the key, the capacitor starts charging. The charge over the capacitor starts increasing with time. This is the equation of charging Q0 1 minus e to the power minus t by tau. We have discussed that Q0 is the maximum charge. You can write Q0 as CE. Tau we have discussed that is time constant. Tau is equal to RC. The dimensions of this RC is that of time. Current is dq over d2. So when you differentiate this equation, you get current I0 e to the power minus t by tau. The maximum current is E by R. So at t equal to 0, if you take t equal to 0 here, then the current, this will be 1, the charge will be 0, and the current will be maximum. So at t equal to 0, your circuit will behave like the short circuit. At t equal to 0, which is usually known as the steady state, at steady state, the charge is maximum and the current is 0. This is all we have discussed. This is charge versus time graph. If you increase time, the charge increases, then it's saturated to a maximum value, and current decreases exponentially. Now we will do discharging of capacitor. So discharging of capacitor, just 1 second, just 1 second. Now we'll do discharging of capacitor. After charging, the next topic is discharge. The next is discharging of capacitor. Discharging means you take a capacitor. It's initially your capacitor is fully charged. Then you connect your capacitor to a resistor and you close the key. So when you close the key, the capacitor starts discharging and the current starts, means the capacitor starts discharging, the charge over the capacitor starts decreasing with time. So the equation of discharging is this: Q is equal to Q naught e to the power minus of t by tau. So here Q naught is the maximum charge. Q is charge at some time t. It's charge at time t. If you want to calculate the equation of current, current is dq by dt. When you differentiate it, you get I is equal to I naught e to the power minus t by tau. So the equation of current is same whether the capacitor charge or discharge. I naught is the maximum current. You can write this as it's E naught by R. That's the maximum current. So this is the equation of discharging. This is how the capacitor discharge. So if you want to plot its charge versus time graph, so initially your charge is maximum, then it starts decaying. If you want to plot the same graph for current, it's time and this is current. So initially your current is maximum and it also starts decaying with time. Current always decreases whether it's charging or discharging, but in charging your charge increases, then it's settled to a maximum value, and discharging the charge keeps on decreasing. So you can discuss the behavior at t equal to 0 and infinite. If I put t equal to 0, what is the value of charge, Nabil Ahmed, if I put t equal to 0 here? What's the value of charge if I substitute t equal to 0? Nabil Ahmed.
Q0, sir.
How much?
Q0, capital Q0.
Q is equal to Q naught. Your charge is maximum. At t equal to 0, your charge is maximum. Because after t equal to 0, your capacitor starts discharging. If I put t equal to infinite here, so if I put t equal to infinite here, then what is the value of charge? Yes, Saifullah, if I put t equal to infinite, how much is the charge?
0.
0. So at t equal to infinite, your capacitor gets fully charged. Sorry, fully discharged. So there is no charge on the capacitor. So this is discharging. Just note it down. We'll do some questions over. We'll do questions exactly from the previous year, sir. Let me.
Sir, is current electricity, right?
Yeah, it's current electricity. So we are revising current electricity. And we're doing those topics which are in JEE syllabus, but not in CBSE. And also that some previous year's questions are JEE. Just give me 1 second. Let me just find that book. Okay, I get the book. Yeah, note it down, please. Meanwhile, I'm finding the questions.
सर वो I नॉट क्या लिखा हुआ है E नॉट अपॉन
E naught upon R. E
सर E
naught
नॉट
upon. E naught is the voltage, the EMF of the cell. Tell me once you have written and scroll it down. Meanwhile, I'll find some questions.
That's
Yes, can I scroll it? Written?
No, 1 minute, sir.
yes.
Done, sir.
It's okay. Okay, so these are few questions from the previous series, which are based on this logic. So usually JEE mains don't ask questions on RC circuit. So the questions that we can find is in JEE advanced. See, like this question, 1982 ID. So calculate the steady state current in the 2 ohm resistor. In the circuit, the internal resistance of battery is negligible and the capacitance of the conductor is 0.25. What does steady state means? Yashika, what does steady state means?
Sir,
Then open
after
it.
some time,
No, not after some time.
So when the capacitor reaches its maximum charge,
Yeah, when the
what current will
capacitor
flow on
reaches,
that?
yes, when the capacitor reaches to its maximum charge. See, we just have discussed when the capacitor. This is the steady state, T equal to infinite. So at T equal to infinite, current is zero. Your capacitor behaves like an open circuit. So the concept that you will be using here is when this is in a steady state, that means your capacitor will behave like an open circuit. It's an open circuit. You can just remove this capacitor. This capacitor is doing nothing in this circuit. It's an open circuit. You open the circuit from here. 2 ohm resistor shown in the figure. The internal resistor battery is negligible. See, if you open the circuit, that this 0.2 microfarad is of no use. This data is of no use here. Just open this thing. So you just have this 2.8 ohm, this 2 ohm, and this 3 ohm are in series. That's it. This is 2.8 or this is 2. This is 28 ohm. You need what you need. You need the internal resistance 2 ohm resistor. Now you can do it. It's easy problem. The steady state, just remove this capacitor, make it an open circuit. You need the current through the 2 ohm resistor. Do it fast. It's simple calculation. Fast. And I'm sure it's not 2T8. It should be 2.8. Otherwise, it's 2.8 ohm. 655. It's 2.8 ohm. Do it fast. I'm waiting for your answers. See, is this logic clear to everyone? Why I remove this capacitor? I removed this capacitor. I made it an open circuit. So it's like this is the arm now. The arm will look like in this way. Just make it an open circuit. Not a simple series parallel question. Answers? Minashi, Noha, Nabil, answers. It's a simple calculation. Okay, I'm solving it. What's the combination of this 3 ohm and 2 ohm? Unib, they are in series or in parallel? Unib is not in class.
Sir, parallel.
Parallel. What's the parallel combination in 3 and 2? It's
Sir,
3
6
into
by
2 by 3 plus 2, 6 by 5. And what is 6 by 5? 1.2. See, this 4 ohm is not a part of circuit now. This 4 ohm is not in circuit. It's an open circuit now. So no current will flow through this 4 ohm. The 4 ohm is not a part of circuit now. You have 2.8 and you have 1.2 here. The total resistance are equivalent on the circuit is 1.2 plus 2.8. It's 4 ohm. You need current. What is current? It's EMF divided by R equivalent. How much is EMF? It's C. R equivalent is 4. So it comes out to be 1.5 ampere.
सर वो स्टडी करंट की वजह से उसको रजिस्टर भी है क्या?
हाँ, steady state की वजह से remove this capacitor, make it an open circuit. If this is an open circuit, तो यहाँ से तो current नहीं जा सकता. तो flow current एक close होना चाहिए ना. If it is an open circuit, तो यहाँ से तो कुछ नहीं जाएगा. 4 ohm हटा दो. So it's 1.5 ampere now. So 1.5 ampere current is passing through this resistor. Will divide into two parts. You have to decide the current passing through the 2 ohm resistor. So what you can do, 3 and 2 are in parallel. The voltage across both will be same. What is the equivalent resistance? It's 1.2. So get the voltage across this whole combination. It's 1.2 multiplied by 1.5. And how much is 1.2 into 1.5? 1.5 into 2 is 3. 1.2 into 1.5 is 1.8. Now this is 1.8 and the resistance is 2. This 1.8 volt is across both the resistors. So across this resistor is also 1.8, across this resistor is also 1.8. So current is, it's V by R, it's 1.8 divided by 2, it's 0.9 ampere. Is it clear, Akshay? Nabil?
Yes.
Yes, sir.
So don't get confused with capacitor. If it have capacitor, it's saying that this is in steady state. That is straight formula based thing. Just remove that capacitor, make it an open circuit, and then you can solve the entire circuit.
Steady state always means that the capacitor will behave like it's not there.
Yeah, the capacitor behaves like an open circuit in steady state. But if it says it's T equal to 0, then T equal to 0, your capacitor will behave like a short circuit. You will remove capacitor and you will place a straight wire over it. Can I scroll it further?
Yes, sir.
Okay, this is over. Next question we'll do. The next question, where is the next question? So even if you look at previous questions, there are very few questions asked on this concept. So the next is this question. Yeah. Question number 17, IIT 2005. Do it. At least try to solve this question. 17. See, in this question, first of all is asking about alpha. What is alpha here? If you write the standard equation is Q is equal to Q naught 1 minus e to the power minus t by tau. So instead of
Tau
1
raised
by
to minus
tau,
one.
you is using alpha. So what is alpha? Alpha is 1 by tau. And what was tau? Noha. Noha is not there. Yashika, what was tau? What was the expression of tau?
Sir, R into C.
R into C. So your alpha is 1 by RC. Now the issue is which R? You have 2 R in this problem. So when you have 2 R, what we do is we first short circuit the cell. Just short circuit this cell and calculate equivalent resistance across the capacitor. So instead of cell, you can assume this capacitor and see R1 and R2 are parallel with this capacitor. So your R here is R equivalent. And that R equivalent is the parallel combination of R1 and R2. It's R1, R2 by R1 plus R2. So instead of this R equivalent, you will use this expression. So this is the value of R. You need maximum charge. What is maximum charge? Maximum charge here is CV. C capacity, V is voltage of the battery. That's it. Note it down. We'll do one last question based on this RC circuit. On Wednesday, we will discuss potentiometer, and this current electricity is also over. Then we'll start with magnetic side. So in current electricity, it's only RC circuit and potentiometer, which is there in JE syllabus, but not in NCERT.
Sir, can you say why we are short circuiting the circuit again?
This short circuiting the cell. The reason is when you calculate this thing tau, then we take resistance which is connected with the capacitor. So when you have two resistance, then it's not very clear whether this resistance is connected to the capacitor or not. To make the circuit clear, we just short circuit. So it will show you clearly that this resistor is directly proportional connected to this capacitor and this resistor also. So when you have whenever you have more than one resistor and you want to calculate tau, time constant, then just short circuit your cell and get the value of equivalent resistance across your capacitor. Tell me once you have written. Yes, everyone have written.
Yes.
Okay, the time is almost over. Do one thing, just write this question number 22. Question number 22 is your homework. On Wednesday, we'll start this JE class. We'll first discuss this question number 22. And then we will start potentiometer. Potentiometer is not in CBSE syllabus, but still in JE syllabus.
Sir, can you send a link for the notes process, sir?
For the notes of chapter 1.
Sir, is it possible to send the ones which are completed till now? Because a few classes have been absent in the middle.
You notes of which chapter, Nabil? First and second, no?
Yeah. Yes, sir.
So I'm sharing. Okay, I'm sharing the whole notebook with you. I'm
Yes, sir,
sharing the whole. So when you open this notebook, you will see all these sections. Just go through the first section, electric charge, and you will find all chapters on all topics of first chapter.
Sir, can you send it on the group?
I'm sending in the chat room itself. I'll send it on the group also. Now it's a very heavy file, so it will take some time to open up. So I've sent the link in the chat room. Yes, Unib, did you get the link, everyone? Nabil?
Yes, sir.
Okay. Okay, so we'll stop here. You can take the screenshot of this